All right, the title of my talk is The Evolution of Lucene and Solr Numerics from String to Points. My name's Steve Rowe. I'm a software engineer at Lucidworks, and I've been a committer on Lucene and Solr for about 6 years. So here's what we're going to talk about, the past, the present, and the future. That's a little bit of a range joke there, that first one. I have a 15-year-old daughter, and when she was 2 or 3, she didn't have vocabulary for times in the past much, but she did know how to say a long time ago, and she knew how to say yesterday. So when she knew something had happened in the past, she'd say both of those together, and everybody knew that was the past. So I think probably what she meant was something like a range, an exclusive range. So neither a long time ago nor yesterday, but sort of somewhere in the middle. So that's my one range joke. What's not on the agenda is talking about geospatial, which probably seems like a bit of an anomaly. That's one of the major uses of numerics in Lucene and Solr, but it's such a large topic that I couldn't really do much justice to it, so I left it out. And I don't know that much about it, so there you go. Ditto for stats, analytics, and streaming expressions, which are covered in every Lucene revolution in more than one talk. So here's the sort of the agenda, I guess. Starting in 2000, when Lucene's first release was done. I think this was either on SourceForge or maybe even pre-SourceForge. Solr's on there too, its first ASF release in December 2006. So what I plan on doing is just walking through some of the highlights of events that have changed the way numerics have been handled in Lucene and Solr. When Lucene first came out, its index terms were strings. And specifically, that format was something called modified UTF-8. So not exactly UTF-8. The differences are down there at the bottom. Null is written out with 2 bytes. There's no null byte ever written out, unlike in standard UTF-8. And UTF-16 Surcode code units are written as 3 bytes. Something that's not part of modified UTF-8 exactly, but the way that it's intended to be used is that counts are in code units. That's UTF-16 chars, and so when you have a length in something that's not exactly the number of bytes, that can cause problems and trigger bugs, that sort of thing. So as you can see in Lucene 2.4 in October 2008, the format switched away from this Java serialization format as the reason it was being used to true UTF-8 terms. And that laid the groundwork to be able to do full binary terms up until the moment they actually need to be used as strings or whatever other format they are, which happened in October 2012 in Lucene and Solr 4.0. Initially, then, since everything was a string, if you wanted to represent numbers, the standard thing to do was just use the base 10 serialization of numbers. That thing that I have there in Solr 1.1, from the beginning, there were several different number types, or at least my experience of Solr. I don't know about before it was released at the ASF. Int field, float field, that sort of thing, was just base 10 string serialization of numbers. So you get a variable with string. The standard advice that was given to people using Lucene was if you wanted to be able to sort numbers that were encoded as strings, you just left zero pad them to a fixed width. And so that sort of advice became tools, first in Lucene and number tools, where base 36 serialization came into play with a fixed width. So it was an attempt to use a few more bits. Base 10 serialization uses just 4 out of 8 bits in a byte. Base 36 is up to like 5 or 6 bits or something like that. And in Solr, the binary coded decimal int and long fields were a base 10,000K integer or long. That could be, it used even more bits of a char where it was stored, but it had quite a bit of overhead of doing conversions between these things. And that was, the BCD type was deprecated fairly soon to be replaced by this sortable field type, which had quite a bit better space utilization there. You can see that the int float long double date and better representation of native types. So a 32-bit ints and floats were represented with 12 bits per char, and 64-bit with 14 bits per char, 3 and 5 bytes when serialized. And Lucene 1.4 in July 2004, a utility called field cache was introduced. This is an uninverted per doc array of native field values constructed at search time. So every time you open a searcher, you have to pay the construction cost for this thing. Once it's constructed, of course, it's quite fast, and you can use the JVM's native sorting capabilities. So questions around being able to sort serialized versions no longer come up. And that, of course, was present in the first version of Solr. The next large innovation was Trie Numerics, also sometimes called Trie range. This is an invention of Uwe Schindler, and it was brought into Lucene at version 2.9 and Solr at 1.4. With Lucene and Solr 6.0, this year, Trie fields have been deprecated with the introduction of dimensional points, and the plan is to remove them entirely from Lucene 7. I suspect, although I haven't seen much discussion about this, that they'll remain in some form in Solr so that back compat on indexes will be possible. So a brief discussion of what Trie numerics are and what they aim to do. The intent was to allow for fast range queries because unlike term range queries, which require enumeration of all terms in between the beginning and end range, Trie range queries could be constructed in such a way that there are far fewer terms. And because there's fewer terms to enumerate and fewer searches to perform as a result, the queries could be much faster. In order to minimize disk footprint, this was and still is 7 bits per byte encoded, so that when serialized to UTF-8, it doesn't blow up into multiple bytes. It has an adjustable precision step, that is the number of bits to shift when generating synthetic terms. So if you look at the diagram down on the right, it's an example of what terms get generated for a set of original numerics. So the row on the bottom there is numbers, and if you follow the lines upward, you can see the synthetic terms that get generated for each of them. So say for 423 synthetic terms, 42 and 4 are also indexed. I skipped one there. Those synthetic prefix terms are created by stripping low bytes and prepending the shift amount in the first byte. So it's not just a shift, it's also got a thing tacked on the front to say which level the synthetic term is on. So when searching for a range, you can see the bracket down there from 423 to 642. The lowest precision terms covering the range or subsets of the range are used. The highlight numbers there are the terms that are generated when a query for that range is performed. So that's just 6 terms versus the 11 that would be required for a term range query. And of course, doc values introduced in Lucene Solr 4, which is essentially a better version of a field cache in that they're constructed at index time and don't require a large amount of memory because they can be swapped out through the OS cache when they're needed. Another important innovation is the flexible indexing that happened with Lucene and Solr 4, which enabled quick turnaround on new formats. Before this was introduced, it was really difficult to get even medium-sized changes to disk formats for the index. But since that's gone in, it's much easier to do experiments and to switch things out and to make faster change possible. Just a couple more things here. Auto-prefix terms was an experimental feature that was introduced in Lucene Solr 5.2, and it was a sort of generalization of Trie numeric strategy in the block tree terms dictionary. You can see there that it was actually removed in Lucene Solr 6.2, just a couple months ago, because of dimensional points, in that it is a sort of not as well optimized version of the same idea and so I'm going to be talking more about points in short order. But the intent was for it to replace Trie Numerics, and there's an issue there that describes how that process was going to happen, but since they got removed, that never did, and also because points has been deemed to be the replacement for Trie Numerics. Yep. So finally, dimensional points. And these were introduced in Lucene Solr 6.0 just a few months ago. What are they? This is my crude attempt at a representation of what the maximal capacity of a point is. Each one of those squares represents a byte, and that could be a single point because points can have up to 8 dimensions, and each dimension can have up to 16 bytes. Once you define a point for a field, all values of that point have to have the same fixed width. Similarly with the number of dimensions. The data structure used to represent this is called a block KD tree. In this disk format and algorithm, the points are sorted and recursively partitioned along the longest dimension. And then once recursion has gotten to the point where the number of points in a cell have been reduced to a target cardinality, the leaf block, as it's called, is written out to disk. And once all the recursive partitioning is completed, then an in-memory binary tree index points to the leaf blocks. This is an improvement over Trie Numerics because the partitioning is adaptive and produces optimal or near optimal balanced tree. Trie Numerics, by contrast, because it doesn't take into account local density, can produce terms that don't represent many terms at lower levels. At this point, points, which some people sometimes call dimensional points, and these terms, I guess, are used interchangeably, are Lucene only, so there's no Solr support. There is a Solr issue on which Tomás Fernández Lobe is doing some work, and I'll mention that later, but at this point, there's no released Solr support. It's optimized for the following query types: range queries, distance queries, nearest neighbor, and point and polygon searches. And all of the implementations in Lucene currently have multi-valued support, so you can, for a given field, index more than one value for a given doc. A couple of things are not supported. One of them is value retrieval, so you can't use it as a value store. The recommendation is to use ordinary storage in order to do that. Also, sorting and faceting are not supported, and the recommendation is to use doc values for these. This is the set of implementations that are currently in Lucene. I didn't distinguish between ones that are in the so-called sandbox, which is a module in Lucene, but a fair number of these are sort of experimental. And I don't think that that means that they're going to be thrown away, but they probably aren't getting much attention, and so may not yet be bug-free, I guess is one way to look at it. With the exception of the binary point, the what I've called one-dimensional native points there, long, int, double, and float, are all fixed width at the width of the native data type that they represent. Binary points can be given any width you choose at creation. And the queries it supports are any and set. This is similar to a terms query where you give a set of terms and then a disjunction is performed over them. Any one of them matching will return a hit. Exact, which is just, at the moment anyway, implemented as a range with begin and end point the same, and of course range there. There are a couple of one-dimensional full width, that is 128-bit point representations, and these have the same supported queries. The big integer point is just what it says it is, with the exception that it's fixed width, unlike big integer in Java itself. So it probably ought to be called a bigger integer point. The inet address point is capable of representing IPv4 and IPv6 addresses. There are these, I think, quite interesting range fields that are there now too, representing ints, longs, doubles, and floats. So you can have up to 4 dimensions of these, and each dimension actually has both endpoints of the range in a single dimension. And the queries that are supported are intersects. That is, there is some overlap in a submitted range. So all of these queries are a submitted range that you're trying to find matches for. So you can find matches where there's some overlap. The contains query will find points that are fully contained within the query range, and within is the inverse of that. 2D geospatial point, there's just one of them, this lat-lon point. It supports within a box, within a distance, within polygon, and nearest neighbor. And finally, the 3D geospatial geo3D point just supports within shape. So that's it for history. I'm moving on to the benchmarking part of the talk. I'm reporting here on benchmarks that were performed by Mike McCandless and Adrian Grand, who did a lot of the development work on points. Mike McCandless in particular worked on implementation of the BKD algorithm and the points format that's included now in the default codec in Lucene. He found in a benchmark he did with his Lucene util project over some OpenStreetMaps data that points were substantially faster at both index and query time than the equivalent trinumeric type. That index size was smaller with points, and that query time heap usage was much lower with points. Adrian Grand reran his benchmarks against a more recent version of Lucene, a 6.2 snapshot, and found that it was 36% faster than Trie at query time, 71% faster at index time, used 66% less disk, and 85% less memory. It sounds too good to be true. And I ran a modest benchmark of a few fixed range queries against 3 different kinds of fields. Trie fields at the default precision step, point fields, and a Trie field with a precision step the same as the width of the field against a long, an int, and a double field that were drawn from data taken from a New York City taxi trips that Mike McCandless had created utilities for in Lucene util. So in the index that I created, I've already said all that, haven't I? Yep. So my thought was these 3 things would represent the main kinds of numbers that are historically present, with the exception, of course, that the trinumerics with the precision step, the same width as the data type itself, is just sort of like a really compact string version. There's no synthetic terms created when trinumerics are indexed that way. So this is the index time that it took on a semi-beefy box that I've got for 25 million fairly short documents with these 24 fields that I list there. String field, 6 string fields, a text field, 2 long fields, an int, and 14 doubles. So you can see the indexing time for points is actually, although it's faster than the Trie fields, and for each of these fields, and it was only the numeric ones that are listed below, for each of these fields, I defined each of the types for each field. So it really is apples to apples in terms of what's being measured here. But just the pseudo strings there, the single precision Trie fields, were quite a bit faster than points. Of course, if you want to do range queries, then just indexing strings is not the way to go. But anyway, index size similarly was best for these really good string types there. These are the 3 fields that I ran range queries. I didn't show them there, but basically they're just fixed ranges, and the hits are the number of hits that it pulled back. I was looking to get a fair portion of the documents when I did it, so we're talking like 1/3 to half of documents are being. I didn't pull them all back with the queries, but that's the number that were hits. And the cardinality of those fields is listed there. So there's a really low cardinality int field there, the passenger count. And for the low cardinality and the high cardinality field, the high cardinality one being the pickup date time, the second one there, points do indeed win on query time. But for reasons that I haven't investigated yet, this medium cardinality trip distance, which is a double, it turns out that the Trie field turned in the best performance. So I guess it's not entirely a slam dunk that in all cases points return the best performance. I should say, of course, that points are fairly new in Lucene and don't exist in Solr yet. And the Lucene guys are working pretty hard to put in optimizations like better compression and faster speed for these things. So it's likely just going to get better from here. Stuff in the future. That's the Solr issue for adding support for point fields. This week, just before the conference, there was a hack day, and I spent a few hours sitting with Tomas, who's been working on this, and Ishan Chattopadhyaya did some work on this issue as well prior to Tomas. And the patch as it is right now just has support for two field types, a double and either int or long, I forget which one. And he's got some pretty good tests set up for it and is working through a couple of small bugs that he's found. There are some components that points don't work with yet, and I think Tomas's plan is to just commit the patch as it exists once he's tracked down the bugs and got those patched, so that there's sort of partial point support committed sooner rather than later. So I expect if he has the time to continue with it, that'll be showing up in Solr fairly soon. David Smiley told me this morning that he will, within the next month or so, be working on adding a Solr adapter for lat long point, which was the two-dimensional point that I listed earlier. Trie numerics are going to be removed from Lucene and 7, so I think I said this before actually, but Solr may take ownership to provide a longer back compat time frame for those. And indirectly related, the field cache may be removed from Lucene, and in that case, moved to Solr. And there's an issue there if you're interested in that conversation that talks about that happening. And I'm at the end of my talk. If there are any questions, I'm happy to entertain them. Oh, and I see Tomas is here, so he can answer all your questions about points. Yeah. It's a good question. The answer is no. In fact, nobody's put in any work to do automatic conversion utilities. Not that it's not possible, it's just there has been no develops there. The advice, as it often is reindex when you want to switch. Yeah.
Sorry, I'm not sure I missed this, but you said there was issues running into migrating, having Solr actually integrate this. Could you elaborate more on what types of issues you guys ran into about putting Solr chasing points instead of the tries?
Yeah. So the question was, what were the problems that led to issues with points replacing trie fields? At this point, there are just some minor failing tests, but maybe you're referring to something else that I said.
Well, that's what I was curious about. Was looking at it didn't seem to be. It just seemed to be a matter of doing it. Didn't seem to be very many open issues.
I think that's true. Right. I think that's true.
Okay.
Tomas, do you have anything to add there?
There is some work to be done for the parameter, which may change.
Thanks. Any other questions? Yes. So points will generate a balanced tree. The cardinality of the one field that, I'm sorry, I should repeat the question. You were asking, is it possible that there's something about the structure of the data that could result in the format on disk being non-optimal for points queries, thus resulting in a lower performance for that one field that I noticed? That's possible. I don't know enough about it to give a cogent answer, but when it's indexed, it'll eventually be merged down to produce a balanced tree. At the moment, the number of values that's in a leaf block is between, I think, 512 and 1,000. So we're only talking about a few blocks here. So the number of tests that's required in order to find a block containing a possible match is very few, like 2 or 3 or something like that. So I'm not sure exactly. It may just be because when a point field search is performed, every single value in a leaf block has to be tested against the query. And as a result, that may dominate as opposed to other, for a medium cardinality field. I just don't know the answer. Any other questions? All right, I guess that's it. Thank you very much.